Hello everyone! This video is the fourth in my series explaining AIME problems. In this video, I'll be talking about problems involving inequalities, sequences, and cycles, and the ways that they can be solved. I encourage you to pause throughout the video and try to solve the problems. There are some prerequisites you should know before watching this video. You should know what arithmetic sequences are and what geometric sequences are, and the sums of arithmetic and geometric sequences, especially the geometric series formula. For example, 1357 is arithmetic and 1248 is geometric. You should also know what the AM-GM inequality is, although I will briefly cover it in the video. Finally, you should know what matrices are and the different ways to calculate their determinants, because this is needed for one problem. For example, you should know the determinant of this 2x2 matrix. Let's start with a problem that involves some simple inequalities. Positive integers a, b, c, and d satisfy a is greater than b, is greater than c, is greater than d, a plus b plus c plus d equals 2010, and a squared minus b squared plus c squared minus d squared equals 2010. Find the number of possible values of a. To start, let's simplify this equation. We get that this equals a minus b times a plus b plus c minus d times c plus d, which equals 2010. But this is also equal to 2010, so these two are equal. Now let's move a plus b to that side and c plus d to that side as well. Then we get a plus b times a minus b minus 1 plus c plus d times c minus d minus 1 equals 0. Now we know that a plus b has to be greater than 0, and so does c plus d, because they're all positive integers. So that means that a equals b plus 1 and c equals d plus 1. From these two equations, we can simplify this again. We get a plus a minus 1 plus c minus 1 equals 2010, or a plus c equals 1006. Continuing onward, we see that to find the number of possible values of a, we need to find the values that satisfy this equation and this inequality. So there has to be a value of b that can go between a and c. So a has to be at least 504, and then c will be 502, so b can be 503. Then we see that a can go all the way to 1004, passing all the integers between, because then c will be 2 and d will be 1. And d can't be anything lower than that, so that's the largest possible value of a. And that's the smallest possible value. So if we subtract the values and add 1, we get the number of possible values that satisfy these equations, which is 501. Another type of inequality problem is an optimization. Find the minimum value of 9x squared sine squared x plus 4 divided by x sine x, for 0 is less than x is less than pi. This problem looks complicated, but we might be able to simplify it. That is where the AM-GM inequality comes in. The AM-GM inequality states that a1 plus a2 plus continued plus an divided by n has to be greater than or equal to the nth root of a1 times a2 times continued times an. In other words, the arithmetic mean of a set of numbers is always greater than or equal to the geometric mean of the same set of numbers. And equality only holds when all of the numbers are equal. Also, this inequality only holds when all of the ai are positive. Now we see that this problem can be greatly simplified. We can simplify this as 9x sine x plus 4 divided by x sine x. And we know that this divided by 2 has to be greater than or equal to the square root of the product of these numbers, which is 36, or 6. And multiplying both sides by 2, we get 9x sine x plus 4 by x sine x is greater than or equal to 12. And we see that such a value can exist from a continuity argument. These two values have to be equal. So once we set them equal, we get x squared sine squared x has to equal 4 by 9. And for all the values of 0 is less than x is less than or equal to pi, x sine x has to be positive. So we can disregard the negative solution and get x sine x equals 2 by 3. Now, how do we know that this value is even possible? Well, for 0, x sine x is equal to 0. And for pi over 2, x sine x equals pi over 2, which is about 1.6. And 2 by 3 is in this range. And since x sine x is a continuous function, 2 by 3 has to be possible as a value. Now let's solve some problems involving sequences. The terms of an arithmetic sequence add to 715. The first term of the sequence is increased by 1, the second term by 3, the third term by 5, and in general, the kth term is increased by the kth odd positive integer. The terms of the new sequence add to 836. Find the sum of the first, last, and middle terms of the original sequence. Let's define the sum of the original sequence as s, and that is equal to 715. Also, the sum plus 1 plus 3 plus 5 continued plus the kth odd positive integer, which is also 2n minus 1, where n is the number of terms, is equal to 836. Now, let's consider this sequence. If you add the sequence, you'll find that it actually equals n squared, and we can prove it in the following way. The arithmetic series formula is the first term plus the last term divided by 2 times the number of terms. And in this case, this equals 2n divided by 2 times n, which is equal to n squared. So this simplifies as s plus n squared equals 836. Now let's subtract this value from this equation. We get n squared equals 121, or n equals 11. So now we know that there are 11 terms in the sequence. So let's define m as the middle term. Then the next terms are m plus d, m plus 2d, continued all the way to m plus 5d, where d is the common difference. And in the other way, it's m minus d, m minus 2d, continued to m minus 5d. And we need to find the sum of m minus 5d, m, and m plus 5d. Then we get that the sum of all of these terms is just equal to 11m, which equals 715, or m equals 65. So m minus 5d plus m plus 5d is equal to 3m, which in turn equals 195, which is our answer. Here is another problem involving slightly different sequences. The sum of the first 2011 terms of a geometric sequence is 200. The sum of the first 4022 terms is 380. Find the sum of the first 6033 terms. So let's start by assigning the first term as a and r as the common ratio. Then, from the geometric series formula, we get a times 1 minus r to the 2011 power divided by 1 minus r equals 200, and a times 1 minus r to the 4022 over 1 minus r equals 380. Dividing this by this, we get 1 plus r to the 2011 equals 1.9, or r to the 2011 equals 0.9, Plugging this value back into this equation, we get A divided by 1 minus R equals 2000. Finally, we can find that the value that we need is A times 1 minus R to the 6033 divided by 1 minus R. And if you plug in all these values to this equation, you get that the answer equals 542. This is a particularly difficult problem that involves sequences of determinants of matrices. Let Mn be the n by n matrix with entries as follows. For 1 is less than or equal to I is less than or equal to n, the entry in row I and column I equals 10. And for 1 is less than or equal to I is less than or equal to n minus 1, the entry in row I plus 1 and column I, or the entry in column I plus 1 and row I equals 10, and all other entries are 0. Let Dn be the determinant of the matrix Mn. Then the sum of 1 over 8 dn plus 1 for n equals 1 to infinity can be expressed as p over q, where p and q are relatively prime positive integers. Find p plus q. Let's start this problem with a little experimentation. The determinant of m1 equals 10. The determinant of m2 is the determinant of this matrix, which equals 91. And the determinant of m3 is the determinant of this matrix, which equals 820. Now, we can see a pattern here that the determinant of the next matrix is 9 times the determinant of the previous matrix plus 1. But we don't know a way to prove that yet. So let's find a general solution, which is 10, 3, and 0 continued. Then 10 here continued diagonally, and 3 continues this way. Then 3 continues this way as well, and 0 all the way this way. And that is our general matrix. The determinant of this matrix, let's say Dn, equals 10 times the determinant of the previous matrix minus 3 times the determinant of this matrix, which is these few rows. But this is the same as the determinant of this times d of n minus 2. So we get that d of n equals 10d of n minus 1 minus 9d of n minus 2. Now, what we're trying to prove is that d of n equals 9d of n minus 1 plus 1. So let's plug that in. Let's say this holds for values under n minus 1, since we know it holds at least for the first 3 values. So we get 9d of n minus 1 plus 1 equals 10d of n minus 1 minus 9d of n minus 2. And this simplifies to d of n minus 1 equals 9d of n minus 2 plus 1, which we know is true because that's what we generalized. So we know that this formula is true, and so is this formula. Now let's try to find a general formula for 8d of n plus 1. 8d of n plus 1 is just equal to 8 times 9 times d of n minus 1 plus 1 plus 1, which equals 72 d of n minus 1 plus 9. And this can be simplified as 9 times 8 d of n minus 1 plus 1. But this is just the previous term. So we get, if we say that b of n equals this, that b of n equals 9 times b of n minus 1. And we know that the b of 1 equals 81. So our final infinite sum just becomes 1 over 81 plus 1 over 729 continued. And from the infinite sum formula, we get this is 1 over 81 over 1 minus 1 over 9, which equals 1 over 72. And this is equal to P over Q, and we need to find P plus Q, which is 73. And that is our answer. Here's the final problem involving a sequence of functions. Let f1 of x equal 2/3 minus 3 over 3x plus 1. And for n is greater than or equal to 2, define fnx is equal to f1 of fn minus 1x. The value of x that satisfies f of 1001x equals x minus 3 can be expressed in the form m over n, where m and n are relatively prime positive integers. Find m plus n. Before we can solve this, it looks like a really long problem because this simplifies as f1001x equals f1 of f1 of f1 continued of f1 of x, and this happens 1001 times, and we surely can't do that. So let's look for a way to simplify this. That is where cycles come in. A cycle is anything that repeats. So functions repeating in values, for example, f of x over 1 over f of x minus 1, and let's say f of 1 just equals 2. Then f of 2 will be 1 over that, which equals 1 over 2, and f of 3 equals 2, and this just repeats over and over. So that's repeating in values. They can also be sequences that repeat, for example, 1, 2, 3, 4, 1, 2, 3, 4, and it's similar to functions repeating in values. And then it can also be sequences of functions that repeat. And the number of times till the same value comes back is called the period. Let's now try to find if this sequence acts like a cycle. F of 2 of x equals 2/3 minus 3 over 3 times 2/3 minus 3 over 3x plus 1 plus 1, which equals negative 3x minus 7 over 9x minus 6 after a lot of simplification. Then f of 3 of x equals 2/3 minus 3 over 3 times negative 3x minus 7 over 9x minus 6 plus 1, which equals x. But then let's try to evaluate f of 4 of x. So f of 4 of x equals 2/3 minus 3 over 3x plus 1. But this is just equal to f of 1 of x. And we know that this is always going to be true because we're going to take the same steps. So f of 1 of x is always going to be equal to f of 3n plus 1 of x for n is greater than or equal to 0. F of 2 of x is always going to be equal to f of 3n plus 2 of x. And f of 3 of x is always going to be equal to f of 3n of x. So we need to find what integer 1001 is. And it turns out that it's f of 2 of x. So this equals x minus 3. And for our answer for x, we get that x equals 5 over 3. And m plus n in this case is 8. Thank you for listening. Please like and subscribe, and remember to click the bell icon to receive more updates.